folks. Sorry about the muting.
All right. I'm 1 minute late. I really apologize. Okay. Who doesn't have a wallet? You have your wallet and you have money in it. Okay, so what are the rules?
Must bet at least $1.
Must bet at least $1. What are the other rules? Have fun? No. This is not a fun class. I don't know what the hell you're thinking. Try. Okay, so some of you have opened your Canvas. Oh, yeah. And many of you haven't. Some of you have been on there for 1 minute, and some of you have been on there for an hour. Now, it could have just been open in the background. I don't mind at all. But you should open it, because we put a rule. I can see everything. I can see what you clicked on. I can see what your favorite soup is. Right? Pozole. I just learned how to make pozole this winter break. I made way too much. I made like a month's. I had to freeze like 9 of these containers.
I feel like you can't make a small portion.
No, that's correct. It was only 8 pounds. It was a minimum amount of shake that I could get. Okay, so here's how the world is going to work. I'm going to post certain things. There's now homework because we have to like try and understand what the hell we're doing. We're not just having fun times in class. And remember that the money that we're using here is an incentive to make the choices that we have in class not just willy-nilly, right? So there wants to be a structure behind it. So there's always got to be a loss. You always have to be able to lose at least something. So we're going to have 3 different types of bets today, and we're going to start off by a card bet, and then we'll do a dice bet, and then we'll play this game. That one has the best. Okay. I made it. You can't see it online, but it's really cool looking, and it definitely doesn't look janky like I made it out of someone's box, like my box. Okay, so the first bet that we're going to remember today, the rules were that since we're only playing for even money, that is, you can only get as much back as you bet, what should your odds always be?
At least 50%.
At least 50%, if not better, right? You never want to make a bet on something less than 50% odds if you're not going to get 50% of your money. Because the goal is to have the most money at the end of the probability and statistics section so that you win some prize A or second up some prize B. Now, no one in the chat said anything about what prizes they want. So I'm leaning towards a $30 and a $10 gift card to the winner's place of choice, but not Starbucks or Trader Joe's. Okay.
What's with the Trader Joe's?
They're a labor dispute right now.
Yeah, I get it.
We're pro-union in this household.
I get it.
Okay, so Jasmine wasn't here last time, so we're going to go ahead and give her the first bet of the day. Now, this is an old bet, so folks who have been here before, do not help her because you don't want her to make money. Okay, and what? That's not nice. Okay, so the guess here is we're going to do the probability of drawing an ace. You know what the cards are there?
Yeah.
Okay, probability of drawing an ace or a spade. And just so everyone sees, last time we did this, I rigged the deck. So this time we have not rigged the deck. Okay. So the probability of drawing an ace or a spade. Now you have cash in front of you. Would you like to play?
Sure. Do I have a choice?
No, you can choose not to bet. You can say pass over me.
Sure.
Okay. Probability of drawing either an ace or a spade. I'm gonna give you one card.
Okay.
And the probability that this top card or whatever, cut it and do whatever you want. Probability that the card that you get is an ace or a spade will give you whatever amount of money you get back. But if it's not an ace or a spade, you'll lose whatever you do. Let's do it. Okay, how much do you want to put it? Just $1?
Yeah, I don't know. I'm new here.
All right, I'm new here. Do you want to cut the deck? Do you want to do anything fancy?
Sure. Let's cut.
Okay, let's cut it. Where do you want to cut? Okay, let's cut it right there. All right, that's your card. Ace or a spade? Yeah, you have to show everyone.
It's a heart.
It's a heart and it's 6. So it's a 6 of hearts, so she loses the $1.
Oh.
Okay, anyone else want to play?
And
why not?
I already know the statistics of it. It's
I already know the statistics of it. Okay, so that's not fair to Jasmine. What's
it's an ace or a spade. Spade, each of the 4 types of cards takes up a quarter of the deck. So you have like, what's it, like 1/4 of 52, I don't know, 13? Yeah, 13, so it's 13, and then any ace, so that's 4 out of 52. But then there's one ace that is a spade, so then it's like 3 out of 52, because it's already been included in the other one. So in total, it's like wait, I can't do simple math.
Okay, so let's do it.
69.
So I like this idea, right? But let's axiomate it, right? So let's put some words down that mean something so that we can all agree on the terminology, and then we'll do probability math. Okay. So you were doing the mathematics, and that's correct.
Yeah.
Let's just formalize it. Let's write it down so that it's meaningful. What's the first axiom of probability?
Sample space.
Okay, we talked about a sample space, but when we're talking just about probability, we're going to say that for any event A in sample space S, we're going to define, okay, this is a definition, that probability of A happening, okay, is going to be bounded. Okay, so it's got to be less than or equal to 1, and it's got to be greater than or equal to 0. That's correct. Okay. So how did we get there? Well, it's because we defined probability as something. How did we define this weird, I mean, we've never really seen, this looks like a function, right, that you might call in like Mathematica or computation or something. You normally don't see it like that. And this is not saying the probability function of A. This is just how we write the probability of A occurring. So we're going to have all these weird little letters that we work on today. I'm going to try and introduce these as we use them. So how do we define the probability of event A happening?
The instances of A over all outcomes.
Exactly. It's the instances of A, the number of A opportunities that I have over the entire sample space opportunities. Okay. Can I use this for anything? Yes or no?
What do you mean?
Yes.
Okay, so here's the things we have to define, right? Can I define a sample space? Remember we said sample space is, when we think about it in the abstract concept, it's a box that includes all possible outcomes, right? So whatever it could be, sample space S incorporates all outcomes. So let's talk about this piece of chalk and its life today. Okay. What are the sample space of the outcomes of this chalk?
Either use it all or you don't.
I could use it all. I could not use it all. So it could end up on the chalkboard. I could drop it, right? Someone could walk out with it in the middle of my class. Someone could run in, like Dr. Clory could come in and say, I need your chalk, and then run out with it, right? These are all the possible outcomes. Now there is an event in the middle, which are the two that you alluded to, the most likely outcomes, right? That event A will be, let's say that I use almost all of this chalk because I'm a really big writer today. Or event B, that I only use like half of the chalk, like down to here, right? So everything that we think about, we can contextualize in this example, right? So this N looks like the number of A events, but you really could think of this as a weight, because sometimes it's not so clear that there's like 6 outcomes that do that, right? So we will be doing some form of counting, but sometimes we will assign like a probability. So we'll say something like, okay, you got a positive COVID result. What's the likelihood that you actually have COVID? We'll have to investigate that today, right? Okay, we'll get to that in a little bit. Okay, so we defined it this way, and just to define this a little differently, what is the probability of S? Why is it 1?
Because that's the probability that something will happen within the.
Yeah. Right, so N of S, right, the probability of this thing here A is the n of A. So this would be equal to n of S over n of S. Okay, done, right? But math has to do that. You have to make sure that all your rules rule, right? We good? Okay. So let's work through your problem really quickly. We had a couple different symbols really quick. So what is this? Probability of A and B. What is this symbol? Union. Union. That's the U for union. What does that mean?
Probably plus B and B.
The probability of both A and B? Or B. Or B. So let's look at the Venn diagram again. Okay, here's S. This whole thing is S. And here's A. Here's A. And here's B. Where is A union B?
Inside.
Everything is at S?
A and B.
Everything is at A and B. So let's do these sideways ones, right? I should have gotten my other colors. I'm sorry. I'll get better. Does it include this?
Yes.
Yeah. Yes, it does. Okay, so we can draw the lines all. So union AB is this symbol in our little circle, right? What about this one? N for intersection, and where is that?
Just the parts where they.
Okay. So this is this, right? So we said the words union and intersection, but you're more likely going to hear what words out of my mouth?
And or.
And or. So let's try to conceptualize those for a second. Let's look at this probability here in the context that we just used it. What is this asking for?
The probability of A or.
Probability of A or B. And what did I start the class with?
Ace or spade.
Probability of ace or a spade. So event A is the probability, or sorry, is getting an ace. Good. And event B is
Getting a spade.
getting spade. Good. So let's compute the probability of A union B. So another way of saying that is what's the probability of getting an ace or a spade? How do I do that? Some people started.
Oh. So probability.
Probability of A plus probability of B, and then subtracting where they intersect.
Okay. How did you know that?
I looked at the book.
It's good to read the book ahead of time, but remember, we do want to tap into our intuition, right? Because what we want to think about is it's perfectly fine to read off the book, right? But what we want to do is we want to say, well, how would I know this if I didn't have my book in front of me? And of course, we can go and we can look at it, right?
Mhm.
But we had some people in the room already starting with a different frame of thought. They were just doing it,
Yeah.
right? So how would you do it if the book hadn't explained it to you?
Just.
The same way, but I guess I would explain the reason why we're subtracting the intersection is
Yeah.
because that's where it repeats.
Exactly. Okay, good. So let's say this again more slowly, right? And let me make John a little louder here. So let's do this. What's the probability of getting an ace?
4 out of 52.
There's 4 aces out of 52 cards. So let's have a look here. There's 4 aces out of the total number of cards. And you assumed, by the way, that that was a full deck.
Mm-hmm.
Did you count the cards?
No.
Okay, okay. We're gonna play with full decks, unless otherwise told. Okay, so this is the probability of getting an ace, and then how do I add? What do I do to the? What's that?
Add the probability for me.
You're gonna add the probability, you're not multiplying?
Yeah.
Okay, so let's do 52 cards again. What's the probability of B?
13.
13.
So there's 13 cards that are spades? Okay.
Yes.
Good, and then what?
Subtract the one ace of spades.
Subtract the one ace of spades, and why was that?
Because they're
We
overlapping.
just double counted.
Just double count it, right? So let's see if we see this properly, okay? This is the number of A, this is the number of B, minus the intersection. So this is probability of A plus probability B minus the probability of A intersection. I'm gonna fuck that up. I'm just gonna cross that a bunch of times. I gotta figure out how to make my A's better. Right? And this is the definition of the use. So what's the answer?
69, 52.
69?
16.
16 out of
52.
52, and that number is. I don't like fractions, I'm bad.
About a third.
It's about a third, so let's do 0.3. And that's less than 0.5. So we should have told Yasmina, don't do it, run. It's a bad gig, right? All right. Is that fair? Okay. Good. Let's do the next one. Let's calculate the probability of drawing from this pack here. Maybe we'll do a card. Does everyone have their dice still?
Yeah.
Did you get dice? Which color dice?
Oh, fuck. Is on my card.
Need your dice. And we'll need the dice twice today. Okay, so let's play a game. Everyone has their dice in front of them?
I'm sorry. I left it at my door. Very irresponsible.
I guess I shouldn't let you take the dice home, huh?
No, I had a pack in San Diego and I didn't want to flip it.
Okay. Folks, you have your dice at home, right?
Yes.
Okay.
Yeah.
And you're gonna be honest about what you rolled?
Yes.
No.
No, you're not. I can't verify that. Okay, so let's do this. I like red. I'm really glad that red is left for me. Okay. Let's make a couple wagers. You're all betting folks, right?
Okay.
So if I have one dice and I tell you, look, let's play a betting game. We'll play for whatever amount of money you want. We're gonna play even odds. But if I get a 5 or a 6, I take your money. You take this one?
No.
No? Yes? Who wants to play?
So if
Hold on. We don't go through the probabilities. You want to do that for yourself.
no,
You
I
don't
was
want to
going
teach
over
anyone.
I was going over the problem itself.
Okay, just on one die,
On one
a
die.
6 or a 5.
Oh,
I
just
roll
on one. Just on one.
a 6 or a 5. You want to play? You want to take that on?
Yeah.
Okay, how much you putting in?
$10.
$10. Ready? 4. All right.
I thought you were in 20.
Yeah.
No. I just said one die. I
Yeah.
just said one die. Anyone else want to play? Oh, everyone, you want to go? Ready?
Wait, let me bet first.
How's your wallet money not out of your wallet? Get that money out. Get that ready to go.
Yeah.
I don't want to show anyone how much cash I have. Okay.
I'll bet 50.
50?
Oh my God.
All right, ready? Ready?
Yeah.
3.
Oh, I'm so good.
All right, very good. Next.
Me.
You can't play, you're not in person.
Yeah, John.
Damn it.
John.
I'm scared.
Be nice. That's literally recorded.
I'll do 5.
You'll do 5? Okay, ready?
$5.
Ready?
So mad.
3.
So anxious.
All right. Dice is fun, right? Anyone else? You'll do 5? Here it goes. Now the weighted die. Two. All right, everyone won. That's interesting. Is that unusual?
No,
Yeah. Yeah.
Why is that not unusual?
because,
You have a.
Yeah, they're in the favor.
What?
Your odds are in favor.
What were the odds?
it was 2 out of 6.
2 out of 6.
2 out of 6 for you. So that's 1/3.
So for me, it was 2 out of 6. So what was it for you? 4 out of 6, right? Because we know that the total probability has to be 1. So sometimes it will be easier to calculate the 1 minus your probability, right? The odds of it not happening. And that's a perfectly good way of calculating odds, right? Or probabilities. Okay, so let's change the game. 2 die.
Same thing, 5 or 6?
Yeah, if I get a 5 or 6 on either. 10? Okay, ready?
Someone bet 100.
Wait, hold on. I got a 1 and a 6.
Oh, you 10, huh?
Yeah. Yeah, you gotta bet something. I gotta make money somehow.
All right,
Daddy needs shoes for the dog.
I'll bet a 10. I'll bet a 10.
Yeah, this is the only money I have. It's my life savings. Look at all this cash. What's that?
I'll take a 10.
A 10?
Yeah, 10.
Okay, ready?
Yeah.
2 5s. All right. Anyone else?
We.
That it?
No,
You can write some stuff down if you want.
Someone go all in.
You gonna go all in, John?
I would.
He's ready to buy back in. He's in it to win it. Isabel did that yesterday or Wednesday. She put everything but the ones. And she made out like a bandit. Okay. Anyone else?
Around there, $10.
10 bucks? Okay, what are your
Bet
odds here?
50.
What are your odds here, folks?
I'm gonna guess it's the same.
You're gonna guess it's the same? Yeah.
Is it the same as divided by 2 for us?
What do you mean divided by 2?
Like, their odds aren't as high because now there's 2 chances.
Yeah, so let's think about how we construct this world of possibilities, right? So here I have a 5. And that was straightforward to get the probability for 1. You did it in your head, right? You just said there's 2 options that will let me lose out of 6 possible options. Okay. With 2 die, how many options are there?
Just 12 options, but for
There's 12 total options?
we're putting 6 sides on each.
Okay.
So then there's 12 total options.
So I could get 1 and 6, and 1 and 5, and 1 and 4, and 1 and 3, and 1 and 2, and 1 and 1. And I could get 2 and 1, right?
Yeah.
It's not exactly just 12 options.
But I meant 12 like sides.
There's 12 sides, good, yeah, there's 12 sides. But we have to know the way in which these samples now play into each other. Because the number of options hasn't grown by 12, it's grown by, no, it's grown to 36. There are 36 options. Okay, so let's see if we can work this one out. We're gonna come back to, yeah.
I think I figured out that.
Yeah, okay. So you can think of this a bunch of different ways, right? one of the easiest ways to think about probabilities, okay, is not to imagine what I've given you, because I am a trickster, right? I am always trying to trick you. You should just assume that, because if I want to take money from you, it's in my best interest to present you with something that looks like it's even money, so that you accidentally take an even money bet, right? And then you lose your money. So I don't want to give you a prize, right? That would be weird. Okay, so instead, let's think about what would happen if instead of 2 die, I took 100 die. And I rolled 100 die, and I only need to get a 5 or a 6 on any one of the 100 die. Would you take that bet?
No.
No, you definitely would not take that bet. Why?
You have a lot of chances to get it.
Exactly. So with every die that you add, you would expect your probability of winning to do what? Decrease. So the question is, how much did it decrease when I just added the first die? So we'll come back to this idea when we do conditional probabilities in 2 seconds. Okay. Now you can do this a couple different ways, or maybe we'll just do it right now before we get into the second half of today's class. So probability of A or the probability of B, right? Is this the right way to do it?
With the die?
Yeah.
No, we multiply them,
Yeah, why would we multiply?
because their outcomes are independent of each other.
Because what?
Their outcomes are independent of each other.
The outcomes are independent of each other. Okay, looks like someone has either been reading the book. Okay, let's define a couple terms. Okay. If I roll this die here, does that outcome affect this die? No. They are mutually exclusive. Okay, so the definition of mutually exclusive is when one, wait, what number am I? Okay. Mutually. One outcome A does not affect you. Right? That's the way we think about that. Okay. If you wanted to figure out these 2 die, you could think about them in terms of a sample space. Okay. So we could write a Venn diagram before we do the probability adding or multiplying or anything else, right? It's not necessarily clear what the outcomes are. So let's tally them, right? That's always a perfectly good way of doing it until it becomes a 90. So if I added a 3rd die, I would not make you do this. But I made a square. So let's do all of the outcomes. So let's do 1, 2, 3, 4, 5, 6. And let's do 1, 2, 3, 4, 5, 6. Okay. This is the sample space, right? This is S. So what is going to screw you over? All right, so this column here. And this one here. And this one here. Okay. How much space is that? A good amount. Okay, so how big is this area here? How many outcomes are there?
12 by 4, so 16.
There's 16 outcomes here. So 16 outcomes where you win.
Now you have 20 outcomes.
How did you know that so quickly?
The multiplicity of a 6 times another 6, 36.
Equal space S has 36 outcomes. So you could have done this two ways. You could have had 12 plus 12 minus 4. That would have been totally fine. That would have gotten you 20. Or you could have said the total number of outcomes is 36 minus 16, 20 where you lose. So 20 losses. Okay, so why did people take that bet?
It was fun.
It's a trick to you, right? No, because it's fun. Sometimes you like to gamble. It's pretty close though, right? It's a pretty close bet. Okay. So there's two ways there to solve the probability problem, right? You can either solve for the probability that it happens, or you can solve for 1 minus the probability that it happens. And that's a perfectly good way of solving. Is that reasonable? Okay, let's do another card. Ready? We're going to do ace, spade, or an even card.
That we wanted it?
Yeah, if you get an ace, spade, or even, you win. Don't write anything down.
I'll do
You
10.
have to work it out in your head. You have to think about this. You'll do 10. Ace, spade, or even. Do you want to cut the deck? You want to do anything fun?
Yeah, sure. Right here.
Oh, right there in the beginning. All right. Ace, spade, or even.
That's spade, yeah.
That is a spade. All right, that's a $10 spade. Spade or even.
Yeah.
And I got a no, a lead, and a shake head.
Oh,
Man, you want to do anything fun? Maybe I should just do this and you can just grab a card. That's the better idea. Right? What is
Well, I got even.
that's even?
Wait a minute.
That's a 7 hours.
Sorry.
That's definitely not an even. How much cash was that? So a loss of 3. A loss of 3. That's okay. That's okay.
I'll bet on it.
All right, we got another bet.
I'll do 20.
A 20?
Yeah.
All right. King of clubs. So
No.
that's a loss of 20.
Yep.
King's not an even. Even's got to be 2, 4, 6, 8,
Yep.
10. Right? Those are evens. Face cards only.
Yeah, face right there.
Anyone else? Anyone wants to stake the farm on this one?
And do it again.
Can't do it again. You can do it again if you wanted. I never said you could only bet once.
I'll do another 20. I gotta.
He made 50 at the beginning of today.
Yeah.
So right now he's down to 20. Net 20.
It's.
There you go. All right, so now he's back up. All right, that was an ace of hearts.
Do it 6 more times, Rolando.
6 more times. Okay, so what's the probability?
So. We got these, we got 1, 2. Let's see.
Okay. Anyone else higher or lower? Now, did you get 62% just because you won?
For the, in our Oz, yeah, that's what it is.
Yeah, I don't know, but is that just because you feel like that's right because you won?
Oh,
Like, how do you know that? Does that feel right?
oh, I feel like I did the math.
That's good. Confidence in one's own work is a skill for sure. Let's do let's write it out. Probability. How would I rate this? Event A is an ace.
Union B.
Union B.
Union C.
Union C. Okay. How's that written?
Not A as the aces, it's 4 to 52.
Even, let's define that here. 2, 4, 6, 8. Only 5 cards, right? No one did an ace, right? Okay. So how do you write this? Sorry, you yours.
So you start with the ace, so 4 to 52.
Good.
Plus the spades, which is 13 to 52. Even 20 out of 52. Then only 2 things have an intersection. I believe.
Yeah, it's the ace of spades and the eve of spades that are interesting.
So the ace of spades, so let's break this down. You are trying to what? Double count or take away double counting? Okay, so you're thinking back to that first union we did, where we had an intersection between the ace and the spades, the ace of spades intersection. And so we don't want to count too many options. So we have to look at where the sample set, let's draw the sample set. Okay, here's the Venn diagram for us to understand. And you see that I make these diagrams, you might be thinking to yourself, wow, that's really stupid, right? Like I've never used a Venn diagram in my whole life. But actually they're quite helpful, right? Because they're gonna let us see where the intersections and the overlaps are. So in fact, I could do this even a little better. I just draw arbitrary circles sometimes, but if we are a little smarter, we can draw a useful Venn diagram. So here's the sample size. There's 52 cards in it. And I draw a little circle. What's the little circle for? Aces, right? A for ace. All right. And then there's the spades. Okay. So let's say a quarter, and I'm not going to do this well. Let's say a quarter of that space is the ace of spades. So what was this bigger circle I drew?
Spades.
Spades. Got B. And is there an intersection between aces and even?
No, aces and even? No.
No, it can't be, right? By definition. So C has to live outside of B, but it does intersect with B. Sorry. C has to live outside of A, but it does intersect with B, right? So there's no intersection with A. So I can draw a similarly sized, now even's a bigger circle, right? But only a small part of it is here. Helpful or not?
Helpful.
Sorry, I was like, I don't know how to do it.
Okay. So let's look in here. So this piece here is
A intersect B.
a intersect B. Good. And this is here.
B intersect C.
B intersect C. Okay, so now if I look at this as a counting, right? If I'm just adding stuff up, how would I do this? So I'd say probability of A plus the probability of B plus the probability of C, right? But now I've counted too much. Like you said, you're going to subtract off these intersections. Minus probability, oops, of A union B, or sorry, A intersect B, and minus the probability of B intersects. And I didn't show this to you, I just told you to look it up in your book. B union C and C union B are the same, right? It doesn't, the commutativity of them. Is that right? Oh, you're right.
Oh, I forgot one of the things, but yeah. I forgot to take away the spade, that's the ace.
Ah, the spade, that's an ace. That's this one, right?
Yeah,
Okay, so this one is a spade, that's an ace. And this one is what?
the 5 evens that are.
The 5 evens that are. So let's do this part, or this part first. Is the spade, that's an ace, that's minus what? 1/52. And this next one is?
5.
Yeah. 5. Okay. And because of this specific example, there is no intersection of all three. But if there were an intersection of all three, what would you have to do? Is
You would also have to minus the intersection of both.
that right?
Wait. No, because you're double again.
And now you're double again.
Yeah.
So now when you do the doubles, right, because this one here, we take the A union B and we subtract it. And then we take the B union C and we subtract it. And let's say there was a union between A and C, we would subtract that as well. And now we have double subtracted the union of all three. Or sorry, the intersection of all three. Let me show you that. So if I write over here, okay, this is going to be our standard Venn diagram. Okay, so I do these two, I add these, I add this. Then I subtract off this one, I subtract off this one, and I subtract off this one. Now I've subtracted too much, and I need to re-add this one. So this is a plus, these are minuses, these are pluses. Does that make sense? Okay. So what's the probability?
Points are 59%.
All right.
Yeah.
Anyone that didn't take the bet? You should be. Rolando took it twice. That's how confident he was. Okay, good. Okay. So we talked about mutually exclusive, right? We defined things that don't rely on one another. We can also talk about this idea of conditional probability. And this is where we're going to use our new box. Okay. So this is a fun game. And this is a game with better than 2-to-1 odds. Okay. Who wants to be the first contestant?
I can do it.
Okay, Rolando is the first contestant of the day in this very well constructed, not janky looking game of a real fun game. Okay. So there are 3 prizes. What you want is the brand new Tesla. Okay. Okay. What you don't want is either this wooden owl from Bangladesh or my teeth.
Why do you have
Okay,
those?
because I only had I had to look for something big that was, gonna work. Okay, you don't want my teeth. If you get behind one of these doors, if you select the owl will take your money and fly off with it.
Okay.
And if you get my teeth will just chomp it all up, eat it all. Okay, but if you get this one, the brand new Tesla, I will double your money.
Okay.
So not even what you got back, I will take 2 times what you got back. Now here's the game. You will select a door. I will not show you what is behind the door. Okay, you'll have your choice locked in. Okay, and then I'll show you a different door. And your job here is to either pick the door that you currently have, the one that you selected, or to change your door choice.
Okay.
If you get the car at any time, okay, so head down. Now everyone, No, heads down. I don't wanna see this eye peeking. Okay. Talked about how good the door handles are. Anything? All right. You ready?
Yeah.
Okay, Rolando, everyone, wake up time. Which door do you want to select and how much money do you want to put on that door?
I'm gonna put. I'm gonna put 50.
You're gonna put 50 on which door?
I'm gonna put 50 on B.
You're gonna put $50 on B, having selected B as the right door. All right. So that means that only A or C could possibly be shown to you. I'm gonna show you. I'm gonna show you what's behind door C. What's behind door C? An owl.
Owl, okay.
Okay, all right. So do you want to stick with your door or do you want to change?
I'm gonna switch to A.
Gonna switch to A. You're confident.
Yes.
Everyone else likes this? You guys know this game already? I know
I
you.
hate it.
I don't care.
John, do you do?
I don't know.
I've seen it once. All right, let's find door A. We ready? We ready? Did you get it right?
I don't know, only you know.
Drum roll. There we go! It's the car!
So good.
All right. So you
Oh,
win
so
$100.
Nice.
Anyone else want to play?
Look at these.
Reed wants to play?
Look at these.
All right, Reed, how much? First, put your head down.
Oh, do we all have to do it?
Yeah, of course you all have to do it. You can't, I can't have you
We're
guys.
changing it every time.
Diluting
Just
it.
the person.
Well, I mean, everything has to change, right?
Yeah, but then our body language won't be cool.
Yeah, right? And you might be like, ooh. Okay. So you got Reed. You're also betting 50. Big spender. And which door are you putting it on?
I go for it.
You're putting it on A. A for alpha. All right, what do you think's in there? In A. Hopefully the Tesla? Right. You think you picked right the first time?
No.
No, you don't think you picked right. All right, so which door do you want to see? Oh, right. Well, in fact, you're gonna see behind B is the owl again. Amazing.
Oh, party bell.
No.
You're gonna lose this. So do you want to stick where you are? Or you want to switch? You're gonna switch?
Yeah.
You're switching me here?
Yeah.
What do you think? I think you just got the teeth, right?
Big mistake.
What?
I just flipped the door.
Big mistake.
I'm getting nervous. You're getting nervous. Are we sure? I think you just got the teeth. You should have stuck.
Yeah, maybe.
What do you think? The owl didn't just like grow wings and fly over there, right? All right, should we see?
Oh my god.
Let's go.
All right, there we go.
Nice.
Anyone else want to play?
Go on, Justin.
Jasmina, you wanna jump in?
And
You can say that.
Stressful.
I'm trying to lose a whole bunch of money. Apparently, both of y'all know how to play. It took me almost an hour. I'm not crafty. You're gonna do 20. Okay, big spender. Yeah, you did. Yeah. All right, heads down. All right. All right, contestant Yasmina, how much money you're putting down? You're putting 20. We're putting this where? You're putting the money on A. All right, and you think that you got it right. 20 bucks on A. Okay. And then from there, I'm gonna ask you, you probably want to switch? Do you want to switch? Everyone else is switching? You want to keep your door? You keep it for now. So let me show you what's behind one of these doors. And just like last time, look who's here. Look who's here. The owl who is behind two. Okay. So now you have more information, right? That affects your outcome, right? Maybe. Depends. You're gonna stick with A, even though they both won by switching.
Yeah.
All right, you think that's a good choice? We'll see. Drum roll. Should she have put more money or less?
Less.
It's the car!
It's rigged.
It's rigged. John, don't be bitter just because you
You're
decided to go to
rigged.
class today. All right, here's what we have. Okay.
Alright.
Anyone else want to play or are we done? This is the most honest game I've ever constructed. I know when I'm
Come
tricking.
on,
Get
get your
okay,
bands
right,
up,
right.
get your bands up.
My bands? I'm thinking about a 15 here. I'm broke.
That's why you gotta get your bands up.
Real life. All right, I'll do 50.
You do 50? All right, everyone heads down. All right.
Watch you lose it.
What did John put his head down in the studio?
Yeah, John is definitely texting folks. That's how I know it's rigged. Now, normally they have an assistant and like a whole curtain and everything. I don't have that. All right, so let me see your money. $50. $50 hairs. And which one are you putting it on?
See.
You're gonna put it on C. This one right here. All right. You sure? Final option for
Yeah, that's fine. Oh, wait, no, I'll switch.
No, but you like putting your original money on C.
No, but I'll do it. I'm
You don't like-
scared.
No, you
It's
gotta,
fine, it's
you gotta
fine.
like it, you
No,
gotta
you
like
leave
it.
it there, it's fine. Fine. If all else fails, pick C, right?
I don't know about that, but that's fair. Okay, so I'm gonna show you a door.
Okay.
Okay, and we've seen the owl too many times. You barely even got a glimpse of my teeth. So here are the pearly whites. Okay, those are the pearly whites. Okay. So you picked the right door? Or do you want to switch?
I'll switch.
You're switching?
Switching.
Whoa.
What about that gut feeling?
D for car.
C for car? John makes a good statistical point.
Not really.
All right, so this is a switch to B.
Yeah,
The B for, oh, you didn't
the
get a car.
Bessie and the Tessie.
Oh, is that what it is? Is that what it is? Okay, let's see. What's in the Tessie? Is it an owl in the Tessie? Or is it my Bessie in a Tessie?
That is insane.
Wow. Okay, so that's very interesting. So what's the strategy here?
Switching,
Why is switching the strategy?
because you're presented with new knowledge that you didn't have before.
Okay, so let's walk through this because this is your homework. You will need to describe to me why switching makes sense. Because here's the thing. I gave you a 1 in 3 probability of picking the right door. And regardless of whether or not I then show you a new door, that original probability hasn't changed, right? So how do you interpret the conditional probability when I show you more information? So this is a problem in conditional probability, and you can do this problem in a number of different ways. You can reason it out with mathematics, you can reason it out with counterfactuals, I don't mind, whatever way your argumentation style is. But here's what you're not gonna do. If you go online, you will see this problem. It's a very easy problem to discuss. People will argue about it both ways. It's a contentious problem. Because instinctually, you will say to yourself, well, I just played it, and 3 out of the 4 times that I played it, I won if I switched. So now your bias might set in that switching is always the right way to go. But we didn't play it a million times, right? So you don't actually know what the true values are. So you need to come up with an argument that is sound and one that'll hold up to scrutiny, okay? You may find this online and think, oh, I can just copy and paste this other person's argument. But that's not what this is. Okay? All right. Okay. So let's talk about conditional probability. We've had some probabilities here. So we've talked about what is the probability that event A happens, right? And now we want to describe what is the probability of event A happening given event B. Okay. So we had one of these things like, what's the probability of, let's do it this way. We did this, I think, the first class. I'm just drawing the 4 aces out. Okay. So here's the example that we're going to use in our mind. We have 4 aces. You can see that there are 4 aces. 2 of them are red and 2 of them are black. Now I'm going to deal you 2 cards. Okay. And the question is, what is the probability that you get a red card? What is the probability that you get a red card? 50-50. If I deal you 2 cards, right?
Yeah.
Wait,
No.
oh, no, but they're both cards.
1 card. If I deal you 1 card, 50-50.
Mhm,
There's 4 options.
mhm.
Okay. Now if I deal you 1 card, it's black. Now your probability of getting a red card goes up or down? Up. Right? And the probability of getting a black card goes down. Here's a thought experiment. You may have seen this TikTok before. You have a vase. I wasn't able to get 100 balls, but you see this idea. You have a vase. Okay. Really well drawn vase. In the vase are 100 squishy Nerf balls. And let's say I drew 100. Okay. The total number of balls is 100. And there's green balls. And there are red balls. The number of red balls is n. And the number of green balls is 100 minus n. Okay. I stick my hand into the pot. I pull out a ball. I look at it. It's red. What's the probability that the next ball that I pull out is also red?
Be in terms of green minus some of the green pulled out for red.
And just let you think about that. So another way of saying this is the next one more likely to be green, more likely to be red, equally likely Well, which one? You have to pick one of these four options. More likely to be green.
You pulled out the red, right?
I pulled out a red, yeah.
I would say green too.
Super green. Okay. Sure. In the lab. Let me cook. All right, online.
I feel like we need more information.
Can you repeat the question?
Okay, I have a vase. It's a metaphorical vase. I don't really own this vase. And it's filled with 100 metaphorical balls, Nerf balls, squishy Nerf balls. Some of which are red, some of which are green. The condition is only that there are 100 balls, that n are red, and 100 minus n are green. So that is to say, some number are red and the rest are green. If I put my hand in and I pull out a red ball, and I look at it, and then I throw it away. When I put my hand in next, am I going to get a red ball or a green ball? And interestingly enough, there's an answer. This is the beauty of probability and statistics. We can understand this problem, as opaque and weird as it is, by starting with the frame of reference that we are using right now, conditional probabilities. Okay, so I'm going to leave this up as a thought experiment. Okay, we're not going to solve it here. But I will say I want to use a problem. Maybe more. Okay. Let's talk about conditional probability for a second. We need to write some mathematics down so that we understand it. And then we're going to do the fun problem where we drive. What?
I said the Tessie.
Yeah, I guess you could drive the red Tessie. Okay, so we were going to write the probability. Where's my... Let's write the probability of A. What is the symbol again? A and B. So we can think of this in the context of the probability of me drawing a red or green ball, given the fact that I already drew a red ball, right? And this is how I would have the and here, conditional probabilities. And I'm going to tell you that it's written like this. The probability of drawing a red ball. So let's imagine this is calculating the probability of drawing a red ball, given the fact that I already drew a red ball. Okay, so that would be the probability of drawing a red ball on its own, multiplied by the probability of drawing a red ball, given the fact that I already drew a red ball. This line here means given. Okay. And
By having both, by having both probabilities there, we're multiplying them together?
Yeah, we're multiplying.
Okay.
Because one is conditional on the other, right? So if the first one doesn't happen, then the second one doesn't happen. So we could say something along the lines of, let's go back to that idea we have here. Okay. A conditional probability. We're going to combine these two probabilities. What's the probability that I wanted to not get a 5 or a 6, right? So what's the probability that you get a 1 through 4? That's 2/3 here. Now this one is a little tricky because it's the probability of B given A. We haven't exactly defined how to write probability of B given A, except that we know that the probability of B is independent of A. So it's going to be the same probability that it would be regardless of A happened. So now we see that the combination of the two, the intersection and, right, requires a multiplication. Whereas OR was a sum. Very good. Right? And you may be thinking to yourself, fuck, what if there's the sums Can't you get above a 1? At least with multiplication, numbers between 0 and 1 never get larger than 0 and 1. But why is it the case that when I do ORs, those also never go larger than 0?
Question.
Yeah.
That notation right there, it doesn't matter if these independent or dependent, like, you can write it for either one.
We're gonna write that in a second. So I was almost done here. This is the same as that. You just switch them. Does it make sense? Right now they are conditionally probable, right? And the way to write this is that in order to write conditional probabilities, the probability of B over A, just using these mathematical identities, would be not over. The probability of B given A
Is it the probability of the intersection over bracket?
All right, so we're going to be able to treat these things as, you know, exactly like they are, like little mathematical terms. You can think about this as a number, 0.5. This is a different number as 0.2 or something, right? That make sense? And similarly with the other one. Okay. In terms of Venn diagrams, you think of the probability of B given A as the probability of B inside of the reduced sample of A, right? So if you looked at the big sample space S and you looked at our circles, then the probability of finding B inside of the reduced sample A. Does that make sense?
Yeah.
And when A is the whole sample, then this is just talking about probabilities. Okay. Make sense? You can also write this here. Let's see if I can do the derivation quickly. Okay. This is a very special time. If two events A and B have the same probability, given that they're conditional on one another, they are mutually exclusive, and their probability is 0. This is the only time. Okay. And in that case, we say that the probability of A union B is equal to just the probability of A multiplied by the probability of B. Now you'll notice that if you just stick that number up there, right? Stick this number up there. So, well, that's not true, right? But this is because we have to define certain things. So this definition is not valid for mutually exclusive events. Okay, so this is the definition of mutually. You can learn how to spell it. Mutually exclusive. Okay. No situationships here. Okay. And this last part at the very end is the definition of what we call statistical independence. Okay, so what do I mean by that? I mean that if I look in nature and I look at the probability of A happening, and I look at the probability of B happening, and then I multiply those together, I should get the probability of A and B happening. Okay, So what do I mean by this? Let's take 2 die. Okay. Let's say these are healthy, normal die that have an equal probability of any one of them happening. Okay, and if I roll them, I should get what? Let's say I want to get 2 6s. How many ways are there to make 2 6s?
It's just the one way, so 1 out of 6.
1 in 6 and
1 in 6.
1 in 6. So the total number of ways is
1 out of 36.
1 out of 36. Good. So that would be if they're mutually independent. And if I rolled them a bunch of times and I only got that result, you know, on average 1 out of every 36 attempts, you'd be like, cool, good die, right? But if I rolled them and there was a little like Wi-Fi enabled counter in here that said, you know, if you're not 6, you know, roll it to 6. Such that after I rolled this one, it told this one to change. Then this would not be true, right? You would need the probability after I roll this of 1 6 times the probability of whether or not it gave that command, right? And that's how you define statistically dependent values, right? This is also how you figure out whether your dice were loaded. Okay. Too long. I didn't even think I thought that I had not enough material today. We're gonna do a fun one. We're gonna do the addition law of conditional probabilities, but I want to put up a picture really quickly and see if we can guess it. Did you guys get this one, by the way? What's the right answer?
I think it's actually green. I think it's green.
Everyone says green?
Green is more likely.
Isabel, what did you say?
Green.
Everyone says green? Except for John, who didn't want to put his cash on the table?
I don't mind switching to green.
You're wrong. Why is that?
Well, I think green because the probability of red is gone, it loses it.
Right,
So
and
it
that
makes
is,
it more likely, but I don't.
so I primed you for that, right? Because I gave you this card problem where you drew off the deck, right? And you reduce the probability. And I think almost everyone starts there. That's a very natural instinct, but it's not right. So think about it this way. Let's say there's a very few number of red balls. Did you just happen to grab the red ball? No. We need to, as physicists trying to understand statistics, understand that the unlikely outcome is unlikely to happen because it's unlikely. And that if we see an outcome that we deem to be unlikely, we throw it away. Does that make sense? There's always going to be outliers in your data. That doesn't mean that your data somehow, oh my God, it's amazing, right? So you get a 5 sigma result, something that really breaks physics, you throw it away first, right? And you keep taking data, okay? So if the ball that comes out is red, right? And you say to yourself, well, okay, there were 100 balls in here. I grabbed one that was red. That's probably representative of the sample. Because it's the first ball that I grabbed. And the chances that there's only one ball that's red in the whole thing and the rest are green is unlikely. You see what I'm saying?
So it's equally as likely.
It's not equally as likely. It's more likely to be red. If the first ball you grabbed is red, it's more likely to be red.
Weird.
Your instincts say that it should be green because you reduced the red population, you threw it out. But what happened is actually the opposite. You got new information about the sample itself. And we'll talk about that when we talk about Bayes' theorem, hopefully on Wednesday. Okay. I was going to show you a picture, but I got carried away. I'll just give you a warning right now. Statistics is hard. And probabilities are really difficult to interpret, to understand. But this is why they're so lucrative. Because if you can do a good job of understanding statistics and probabilities when other people don't, that's when you're going to thrive, right? Okay.
the Wednesday homework is due at the start of class? Like, do you want it?
Yeah, I don't know. I guess, yeah, try to turn it in on Wednesday. It's not that hard. It's one problem. It's just explaining the Montreal problem.
And then you want it, like in person, turn it in person or like over campus?
No, in person. Always written out, please, in relatively good handwriting.
Okay.
You have your cash?
Yep. Should we count it first?
No. If you put it in your wallet, then it's not separated, or it's separated. I want it. Yeah, I'm gonna keep your wallet. Because if you don't come to class or whatever. It's fun though, right?
Yeah.
We're having a good time?
Right.
No one's cried online, right?
So fun.
That's what it was
Super
saying.
fun.
Super fun. Can't believe everyone invested my money all for this.
Me and Trinity were talking
Four
about
for four.
it in the morning. Like,
You
I was
were?
like, I was like, oh man, we have homework due Wednesday, so I looked at it.